Did you know that the Earth's magnetic field serves as a vital protector for life on our planet? The Earth's magnetic field is the largest magnet in our vicinity. Thanks to the presence of molten iron and nickel inside Earth's core, as well as the angular rotation of the Earth acts like a large, permanent magnet. This magnetic field, known as the magnetosphere, has the ability to repel solar winds composed of energetic plasma particles. The solar wind is created by the outward expansion of very hot charged particles, called plasma, from the sun's outermost atmosphere. Without this protective shield, these high-energy plasma particles could potentially strip away our atmosphere, leading to a fate similar to that of Mars. Now, if you are interested in learning the basics and fundamentals of electric fields and magnetic fields and understanding how they work, stay with us until the end of the video. If you enjoy our video, please make sure to hit the like button and subscribe button to our channel. Let's embark on a journey through the history of science, beginning with a figure whose work has left an enduring mark on the world of physics and beyond. Michael Faraday, one of the most distinguished scientists, played a pivotal role in shaping our understanding of electromagnetism and electrochemistry. From the remarkable discovery of electromagnetic induction to the intriguing concept of diamagnetism, Faraday's contributions have truly revolutionized modern life. Let's dive in and explore the genius of his scientific discoveries. Building upon Faraday's foundational work in electromagnetism, let's start with a quick introduction on how electric forces function. The electrical force, similar to other forces, is commonly measured in newtons. As a force, the intensity of the electrical interaction is a vector quantity that possesses both magnitude and direction. The direction of the electrical force relies on the charges of the objects involved, whether they are of the same charge or opposite charge, as well as their spatial arrangement. Let's look at the simple example provided below. In the given illustration, both particles possess like charges, resulting in their repulsion. Nevertheless, when two particles have different charges, they are attracted towards each other due to the attractive force between them. The force field between charged particles is known as Coulomb force. Coulomb's law calculates the magnitude of the force between two-point charges separated by a distance r. In this equation, Q and Q2 are the magnitudes of the charges of the two particles. The K is the Coulomb constant and R represents the distance between the particles. In SI units, the constant K is equal to 8.988 to the power of 9 Newton meters squared per Coulomb squared. Now, let's shed light on the space between the two-point charges. The animation illustrates how the electric force is depicted in this space, using field lines shaped like arrows. These arrows not only show the direction, flowing from positive to negative charges, but also convey the strength and pattern of the force. Originating radially from the positive charge, they arc gracefully, bending as they're drawn toward the negative charge. As you'll notice, the proximity and density of these field lines directly correlate with the intensity of the electric field. The closer and denser they are, the stronger the field. Now, if a third charge carrier is positioned in this electric field, a force acts on it in a direction tangential to the field line where the charge carrier resides. If the charge carrier is positive, the force acts in the same direction as the field lines. Conversely, if the charge carrier is negative, the force acts in the opposite direction. When examining the various types of electric fields, there are several additional ones we will cover here. For example, there's the radial field that forms between a central charge carrier and multiple surrounding charge carriers of opposite polarity. Another type is the homogeneous field, which is evident between two capacitor plates. The homogeneity of this field is characterized by the parallel alignment of the field lines. If you're keen on learning more about capacitors, we have a dedicated video on our channel that delves into the basics. Now, let's explore the relationship between the parameters we discussed earlier and see how they can be incorporated into an equation. In the SI system, electric flux is denoted by Q with units of Coulomb. The strength of the electric field is represented by E, has units of newtons per coulomb or volts per meter. Additionally, electric flux density is symbolized by D and is measured in coulombs per square meter or ampereseconds per square meter. The dielectric permittivity, represented by epsilon, describes a substance's ability to store an electrical charge. Its unit is farads per meter, which can also be expressed as ampereseconds per voltmeter. The electric flux density can be calculated by multiplying the dielectric permittivity with the electric field strength. Furthermore, the strength of the electric field can be determined by dividing the force by the electric charge. To visualize a magnetic field, a simple bar magnet is an ideal example. Every magnet inherently possesses both a north pole and a south pole, with magnetic field lines running between them. These field lines emerge from the north pole and enter the south pole. A magnetic field is produced by either a magnetic object or a changing electric field. This field consists of lines of force that circulate around the object or charge, creating a three-dimensional pattern. For illustration, it's helpful to focus on the field between the two ends of separate bar magnets, analogous to how electric fields are presented. As demonstrated in the animation, when two magnets with opposing poles face each other, they experience an attractive force. This attraction amplifies as the magnets approach each other. On the other hand, identical poles repel each other when brought closer together. Now, let's explore the equations associated with the magnetic field. The strength of a magnetic field is denoted by the symbol H and is measured in units of ampere per meter. The magnetic flux density is represented by the symbol B and is commonly measured in Tesla or Gauss, with 1 Tesla being equal to 1 Weber per square meter and 1 Gauss being 1 per 10,000 of a Tesla. The calculation of magnetic flux density involves multiplying the magnetic field strength H by the magnetic permeability or mu, which is expressed in Henry per meter. Permeability serves as an indicator of a substance's response to an externally applied magnetic field. By now, you might be wondering about the primary differences between electric and magnetic fields. One significant difference between electric and magnetic fields is that electric fields are associated with the presence of electric charges, while magnetic fields can exist even in the absence of magnetic sources. Furthermore, forces exerted by electric fields align parallel or anti-parallel to the field lines. In contrast, forces within a magnetic field act perpendicular to both the field lines and the velocity of the charged particle. In summary, electric and magnetic fields are distinct phenomena, each with their own unique properties and behaviors. Although they share some similarities, such as the presence of field lines, they originate from different sources and interact differently with charged particles and magnets. Understanding these fields is crucial in understanding electromagnetic phenomena and their applications in various fields of science and technology, which we will cover in the next section of this video. Building on Faraday's groundbreaking experiments, James Clerk Maxwell became the architect of electromagnetism's mathematical foundation. His genius lay not just in his exceptional mathematical skills, but in his ability to see the unity in the science of electromagnetism, a field that, until his time, was fragmented into isolated phenomena. Maxwell's equations, as they are now known, are like a master key, unlocking the mysteries of how electric and magnetic forces work together. They form the backbone of many modern technologies, explaining everything from how a light bulb illuminates to how a phone communicates. In essence, these equations show us the dance between electric charges and currents and the fields they produce, revealing a world where electricity can create magnetism and magnetism can create electricity. The first equation, known as Gauss's law, states that the electric flux through a closed surface is proportional to the total electric charge enclosed within that surface. In simpler terms, if you imagine a closed surface as an invisible bubble, Gauss's law tells us that the net flow of the electric field passing through this bubble surface is directly related to the amount of electric charge inside the bubble. If there are no charges inside the bubble, then there will be no net electric flux through its surface. The second of Maxwell's equations is often called Gauss's law for magnetism. It states that the net magnetic flux passing through a closed surface is zero. In simple terms, this law tells us that magnets don't have a single north or south pole. They always come in pairs, what we call a magnetic dipole. Let's use a bar magnet as an example. It has a north pole and a south pole. According to Gauss's law for magnetism, if you try to separate these two poles by cutting the magnet in half, you won't get a north pole in one piece and a south pole in the other. Instead, you'll end up with two smaller magnets, each with its own north and south pole. No matter how many times you cut the magnet, you will always get smaller dipole magnets. This is different from electric charges, where you can have just a positive or just a negative charge. The third equation, known as Faraday's law of induction, states that a changing magnetic field induces a circulating electric field, causing electrons to move. This phenomenon is referred to as magnetic induction. Let's consider a simple example of this electromagnetic induction mechanism. When a magnet is moved across a copper coil in any direction, an electric voltage is generated. Subsequently, this voltage produces an electric current that can be detected with a galvanometer. If the magnet's movement within the coil is faster, the change in the magnetic field induces a higher electric voltage. Moreover, when the magnet is moved in the opposite direction, the induced voltage reverses polarity. The direction of the induced electric current always opposes the initiating change, a concept known as Lenz's law. This means an induced current will always counteract the motion or change that produced it. A key principle in the study of inductance. This phenomenon, central to Faraday's law, has been utilized by scientists and engineers to convert mechanical motion into electricity. This technique is widely employed in power generators, from wind turbines and nuclear power plants to telephones, transforming mechanical motion into electrical energy. The fourth equation, commonly referred to as Ampere's law with Maxwell's addition, provides a comprehensive understanding of the fundamental properties of electromagnetism. It reveals how electric currents and changes in electric fields induce a magnetic field, and how a changing magnetic field induces an electric field. This can form a continuous cycle of electric and magnetic field induction and gives rise to electromagnetic wave. An example of a changing electric field altering a magnetic field is found in the operation of a capacitor during charging or discharging. As a capacitor charges, its accumulating electric field between the plates changes, inducing a circular magnetic field around them. This interaction, where a changing electric field produces a magnetic field, was Maxwell's critical addition to Ampere's law. This dynamic interplay creates an interconnected relationship with Faraday's law of induction and forms the basis of electromagnetism. But what exactly is the nature of electromagnetism? Electromagnetic waves consist of synchronized oscillations of electric and magnetic fields that are perpendicular to each other and to the direction of wave propagation. The electromagnetic spectrum can be characterized by either its frequency of oscillation or its wavelength. The rate at which the fields alternate determines the frequency of the electromagnetic waves, while the amplitude of the fields determines their intensity. Electromagnetic waves of varying frequencies are given specific names based on their origins and interactions with matter. These waves are categorized in ascending order by frequency and descending order by wavelength. Starting with the lower end of the spectrum, we have radio waves, which range from a frequency of 3 Hz to 3 MHz. You can find the radio waves application in radio stations, television sets, and your cell phone. Next in the line are microwaves, with frequencies spanning from 300 MHz to 300 GHz. Microwaves are commonly used in household appliances like microwave ovens. Following microwaves, we have infrared radiation, commonly found in remote controls with a frequency range between 300 GHz to 400 THz. As we progress along the spectrum, visible light emerges with a frequency range of approximately 430 THz to 750 THz. This particular range, encompassing visible light, represents the sole spectrum perceptible to the human species. Beyond the visible light spectrum, we encounter harmful radiations, with ultraviolet radiation being more intense than the aforementioned wavelengths, ranging from approximately 750 THz to 30 petahertz. The sun is a primary source of ultraviolet radiation. X-rays constitute a segment of the electromagnetic spectrum, with frequencies ranging from approximately 30 petahertz to 30 exahertz. They're characterized by a shorter wavelength than ultraviolet rays and a longer wavelength than gamma rays. Doctors utilize these rays to capture images of our bones with X-ray machines. At the far end of the electromagnetic spectrum lie gamma rays, with frequencies exceeding 30 exahertz. These rays possess a high level of energy and are commonly detected in the context of nuclear explosions. We hope this was an enthralling journey that showcases the harmonious blend of theory and application in our universe. If you enjoyed our video, please make sure to like and subscribe. We look forward to seeing you again in our upcoming videos. Goodbye.